Hi guys, and welcome back to the Science Jam, where I, Jemiah, make technical topics fun and easy to learn. So, if you all tuned in to my last week video, you will know that what I'm going to be talking about today, right? But if you didn't, I'm just going to go ahead and tell you. Our topic is, why do bridges collapse? Because unfortunately it is something that happens, but today I'm going to be telling you why this happens and everything behind it. So today we're going to be talking about what deflection is and what deflection looks like. We'll just go ahead and get into it. It is, let me tell you, one of my favorite Greek letters to draw, just because it's all squiggly with the motions, okay? Looks just like that. Can you see that? Now you got it. And deflection is the difference between lengths. So let's say we have a spring. It's an average, normal looking spring, and it looks just like this. And we're going to say that this is length original. So we're going to dictate that with L original. But let's say we take this same exact spring and we stretch it out. So now it looks like this. Just a few more squigglies. And we're just going to say that this length is length L, because at the end of the day, I'm not sure how far we stretched it, but we stretched it. So we're just going to dictate it with length L. And all that deflection means, it's just the difference between lengths. So deflection is just L original minus L. So you're probably wondering, okay, cool. So deflection is the difference between lengths, but what does that have to do with bridges, you say? Well, with bridges, we change the lengths whenever we pass over a bridge, but even smaller than that, just when a bridge is remaining stagnant, just by the wind blowing on it, changes the length, even if it's just a little bit. Either way, there's still a force being applied to that bridge, and whenever a force is applied too much, that's when the bridge collapses. Or better yet to say, whenever the force exceeds the safety factor, because at the end of the day, bridges have safety factors in which engineers have to take into account. So, what do we already know? We already know that deflection is the difference between lengths. So we know that deflection is this right here, L minus L, L original minus L. But, as I mentioned, we can also find out how a material is feeling based off of the stress and the strain. So, and that is what we more so care about, because in order to find the strength required for a material, we need to find the stress and the strain. So, from the deflection leads to the stress and the strain. From the strain leads to how a material is feeling, and which then eventually leads to whether the bridge falls or whether the bridge collapses. Does that make sense? One thing leads to another, but first we have to start with the basics, okay? So, what strain is, it's epsilon in Greek. It's also another fun one to draw. You guys should probably just try drawing Greek letters. It's actually way more fun than the alphabet. Strain is dictated by epsilon, which looks a little bit like this. Well, not a little bit, it looks exactly like this. And what strain is, this is Greek in epsilon. This is epsilon in Greek. And what strain is, it is the change in length over the original length. But wait, didn't we just say that deflection is the change in length? So, we can now say that epsilon, the strain of our material, is the same as deflection over the length of the material. The length, not original length, but the length that we stretched it out to. Okay? So that's great. Cool, Jemiah. So what does deflection and strain have to do with a bridge falling? What does that have to do with anything? Well, I'm going to tell you. So, like I said, deflection is now related to strain, but how is strain related to stress? Because these are two mechanical properties that we're going to find out today, and what they are doing and what you are doing to this beam, because you're making this beam sad. Okay. Anyway. Now we have the stress of a material, and what the stress is. Stress is represented by delta times the strain of the material. So with this capitalized E is dictated, this is our modulus of elasticity. And I know that sounds so super duper crazy, modulus of elasticity, you know, but all it means is it's the hardness of a material and just how hard it is, because you know that we have brittle materials and we have ductile materials, you know, materials that are harder than others and that have, you know, higher stress factors and can, you know, withstand a higher force before fracturing, right? So that's all that this E represents, this right here. So the modulus of elasticity times the strain equals the stress of our material. So now we know how the beam is feeling, right? We know how to find out what it's feeling. If only it was that easy for people, you know? If only there was an equation that would say, Jemiah's feeling rather sad today, but how sad is she feeling and what can I do to make her feel better? You know, if only things were that simple. I guess that's why I like I like beams more than people. They'll tell you how they're feeling. I'm gonna get into a problem, and what that problem is, it's gonna be asking me to select the most convenient beam. But in order to select the most convenient beam, I need to know a few things about this beam, because at the end of the day, I know this may sound crazy, but beams have feelings. It's kind of funny how materials have feelings, you know? Materials have feelings because atoms have feelings, you know? Whether atoms are colliding or whether they're being together, they all have feelings, and so whenever you're passing over that bridge, it feels you. It feels you. Yeah, so materials have feelings, and they're called stress, they're called strain, they're called shear stress, they're called all of these crazy mechanical properties that we know about, or that we are about to learn about. I want to do a bridge problem, or I'm going to simplify that a little bit more, and it's just going to be a beam problem. Because whenever you're looking at beams, there's so many different things that you can find out about it. You can find out the mechanical properties of a beam, because beams have feelings too. I know it's crazy, but they do have feelings. And we can represent how a beam is feeling, or how a material is feeling, based off of its mechanical properties, such as its stress, its strain, the hardness of the material. And how we can figure that out is by doing a shear and moment diagram, which I'm about to do in just a moment. If y'all would like for me to get into shear and moment diagrams a little bit more, just comment down below and I will make a video on that. But for right now, I'll make sure that I am the one who is doing all of the crazy complicated math behind everything, and you all just sit tight and watch me do that. So basically, what that has to do with deflection is that deflection is, we can find out what strain is from finding out our deflection. But this is how we're going to do that. If our strength is greater than our strength required, then we're okay, and our bridge will withstand, and this mechanical property is fine, and this beam that we have selected is fine. If not, if our strength is less than our strength required to withstand this force, then we need to select a different beam, or in perhaps the real world, if we did not select a different beam, that bridge will fall. So let's look back at our example and see, is our bridge going to withstand, or is it going to fall? So here right now we have our maximum moment is 75. Our strength required is 30 KSI, which then gives us a strength required of 75 over 30. What is that? Quick! I don't know. I'm gonna look at it in my calculator. I'm gonna calculate it. 75 over 30. 2.5. Wait. Why didn't I know that? Because 30 plus 30, that's 2. 15. 2.5. Why did I do that? You guys are gonna think I'm so dumb. The bots in the comments are gonna be like, oh, she's an engineer, but she doesn't know 75 over 30. Well, baby, let me tell you, when you get to the back of the book, you have forgotten what is at the front of the book. Let me tell you that much. Anyway, back to what we were doing. So, 2.5. So let's say that our strength for this specific beam, mainly what we do in the real world is we use tables just to see what the classification is of that beam. But for now, I'm just going to make it up and say that the strength required is 2.5, but the original strength of our beam is 2. So in this case, since our strength required is less than the strength of the beam, it is going to fall. I'm dead. You know? It's funny. No, it's not. Anyway. But yeah. So our bridge is fallen. I have fallen on the ground, clearly. And now you know what deflection is and what that has to do with bridges collapsing and bridges standing up. Alright, you also, just to wrap it up, I'm just going to go over what we learned today. We learned how deflection ties into the strain of the material, how the strain ties into the stress of a material, how the stress ties into finding the strength required of the material. But in order to find the strength required, we also need to find the maximum bending moment. And how we find the maximum bending moment is by using our shear and moment diagrams right here. Like I said, if you want a video on this, just down in the comments below, I can explain how I did this and how I got the maximum moment. But at the moment, we're just gonna skip past all of that, all of that hard stuff. And then, so since we found our strength required, we then went to our table to see what is the actual strength required. And if our strength that we found is less than the actual strength, we know that we are fine. Our bridge is going to withstand. But in this case, our strength required was greater than the actual strength of our material. So in this case, our bridge failed and it collapsed. Which is not good. We do not like that. We do not want that. So since that happened, we just need to pick a different beam, right? A different material, one that is more ductile, one that has a greater modulus of elasticity, which we learned is the hardness of a material. So there we go. That's it for today. Check back in next Sunday to learn a new technical topic where I, Jemiah, make technical topics fun and easy to learn. Thank you all for watching. Make sure you comment, like, and subscribe and share, and I will see you all next week. Thank you so much.